So ranges V3 and microcontrollers, right? Rather than telling you who I am, I'd rather talk really quick about what's important to me. And I'm sure most of you have probably heard of the innovation valley of death. Over here on this side, we're iteratively improving candles, and over on this side, we're figuring out how to make vacuum chambers and electricity, and nobody's building light bulbs, right? And this has a negative effect on the stuff over here more than it has over here, because people dropping papers and walking away, okay, well, is that paper correct? And there are multiple ways of proving that, and one of them is actually building it and seeing if it works, right? And that's obviously not the only way, and maybe not even always the best way, but it's a good feedback loop, right? And if this takes 20 years, that's not a feedback loop, right? So if you want a lot of money, then work here. And if you want a lot of job security, as in if you stop coming up with good papers, well, we could just play bullshit bingo and, well, nobody will figure it out for 20 years, right? If you want to be useful, work here, right? And to a lot of you, I'm preaching to the choir. You're part of the standard committee, which is pretty much unpaid, right? And you're doing hard work and nobody's paying you for it, right? So this is me trying to be useful. I haven't invented most of this stuff, the vast, vast majority of this stuff, and this is not a library you can put into your code tomorrow because it hasn't been hard tested, and a lot of it's just proof of concept. But in the interest of releasing early and often, and convincing you that you should be compiling your C code with C++ today, because there's stuff in the pipeline. I know there wasn't for 30 years, but there's stuff in the pipeline that's going to change the way we do this. So what was I talking about? Yeah, Eric Niebuhr, he's cool, right? And microcontrollers. Shit, I have to explain microcontrollers. So here's a comically fast explanation of what microcontrollers are and what the design constraints are, right? So you drink some of this because you have to be highly caffeinated, and then you take the bottles back to the store with small change, you buy one of these. Not the golf ball, that's way too expensive. You'd have to take back way too many bottles. That tiny chip on there that costs a couple of cents, right? And the core of the chip is actually now very tame, right? It runs thumb 2 instructions, right? Just like the big arms. But it's not just a core. There's also peripherals, there's RAM, there's all sorts of stuff on this chip. It's not just a processor. And to interface with these peripherals, we have what's called special function registers, which to the core and to the compiler is RAM. It's just some address that I can write stuff to and read stuff from. But it's hardwired to hardware, right? If I write a 1 there, that LED goes on because that pin gets driven high, right? And the optimizer doesn't understand any of this. And, well, neither do we most of the time, but the optimizer is built to not understand this, right? And so we have to use volatile, right? Volatile, right? So hands up, who understands volatile? Okay, we don't have time to go through that. You're all wrong. What Chandler here? No, you're all wrong. It's implementation defined, right? The compiler, like the standard, doesn't say any hard and fast rules about volatile. The compiler can decide what volatile means, and so it depends on the compiler you use, and it also depends on which version of that compiler you use, and the phase of the moon, and all sorts of other stuff, right? And so this makes serious tool lock-in, right? This is one of the reasons we have serious tool lock-in in this domain. Because, yeah, you turn on link time optimization and, oh, wow, a lot of my code disappeared, but a lot of it doesn't work too, right? Go find that, have fun. Your boss won't pay for it, I'm sure, right? So the problem with this lock-in is that we haven't had innovation in a long time, right? We also have 1,000,000 times less RAM, right? 6 orders of magnitude. Like on a desktop, okay, you have 4 gigs of RAM. We have 4K of RAM, right? You have maybe 16 gigs of RAM. That's a big chip, right? A big system, right? Well, we have 16K of RAM. I mean, okay, we could argue if it's 5 or 6 order of magnitude, but that's not the point. We care about memory in a very different way than your typical C++ developer. I mean, that obviously doesn't exist, but yeah, we care about RAM in a different way, and so very subtle inefficiencies turn out to be huge, right? I mean, 1 million, right? Yeah, so let's play around with some math, right? So we all understand how schedulers work, right? Well, probably not, but yeah. So if I have a scheduler, I have essentially a stack for every thread. We haven't really had to think about the stack since like C made it mandatory back before I was born, but the stack grows in stack frames. Every time I call a function, that function's local variables and where it returns to whenever it goes on the stack, right? So I have this thread calling functions. Okay, that one returned, calls another function, adding more RAM to the stack. Oh, and then I have a context switch. Now I'm in this function. And then it adds, and then some return, and then it adds more. I have 6 of these, and I also have interrupt service routines, right? Interrupt service routine, for those that are not deeply embedded, essentially something happens and I have to react to it really fast, so I just context switch into that thing, essentially, right? So, some ping goes high and I say, oh no, that's like the emergency override, I have to do something, right? That gets put on the end of whatever stack we were in, right? Interrupts don't change the stack pointer. We just add to the stack we're in. When we're done with the interrupt service routine, we come back and then do whatever we used to be doing, right? So if I want to calculate, just in this naive example, how much RAM do I need for this, right? Well, I can be calling along, get to my absolute worst case nesting depth in this thread. It could be interrupted by the lowest priority interrupt. I keep adding, get to my 5 instantiation, or my 5 call depth. It gets interrupted by the next higher priority, so on and so forth. So I can essentially add these together, right? Like 15 and then 10 is 25. And then that, every thread could be interrupted. So in the very worst case scenario, it could be any of them. So all of their stacks have to be big enough. So I have 6 times 25 stack frames. Well, what's the minimal size of a stack frame? It's implementation dependent, but on ARM, like a call automatically pushes your first 4 work registers to the stack. Then you also know where you need to return to and how big the stack frame is, right? So 6 ints or pointers or however you think about 32 bits of data on a 32-bit processor, right? But the thing is, with 4K, we only have 1,000 ints, right? So with any minimal, OS stuff, we filled up the chip just with stack, right? That's obviously not the right way to do it. So what do we do, right? Well, we could not use a scheduler. I mean, there's a lot of other tricks. Like we could make an interrupt-only stack, and that would kind of mitigate the problem because we do a context switch like implemented in our interrupt service routine and would increase our interrupt latency, which we spend a bunch of money on a chip to like reduce. And yeah, but essentially, if we just had, one stack, right, and our state modeled our program as a state machine, we could get around this problem, right? We could use a lot less RAM doing it. We could also obviously inline stuff. We have a similar problem with the heap, right? If we're allocating small objects to the heap, the bookkeeping stuff is going to be maybe even bigger than our object, plus we can have fragmentation. I mean, again, like with the stack example, I'm probably never going to see that worst case, right, where everything gets interrupted at the exact right spot. But it's theoretically possible, right? The other question is, how do I prove that I only have 10 nesting depth? Function calls a function calls a function, right? After optimization, obviously, right? And if I prove that, there's a butterfly effect, right? I change one tiny thing, and then suddenly it's no longer in line, and suddenly my stack grows, right? And there are tools to do this. If you reduce the set of things that you use, you can like no indirect calls and stuff. Then you can just analyze the assembler, right? You cut out the middleman. The compiler interpreter is probably move fast, break things, right? So it could change. My code could change, all these butterfly effects, but if I just analyze the assembler, then I can prove that I can't stack overflow. And there's a company that does this, Absint, analyze your thing, cost 40K, and that's obviously easy for a startup, right? So what are the other options? Well, if I just had one stack, I can make it grow into RAM that doesn't exist, and then at least I get a defined thing happens when my stack overflows, rather than just growing into other data and corrupting it, right? Because, you know, yeah. So that's, you can't use a threading model anymore if you do that, though, right? And, you know, the world works in threads. Everyone knows that. Like, if there's not p threads down there, it's wrong. But, hi, Jackie. So there is a third option here, and it's the most popular by far. You guess and pray, right? Like, you know, you say, okay, I had a stack overflow. Let's double the size of the stack, right? And, you know, okay, maybe there's 2 1 a million things, and only when they happen at the same time, then I will actually overflow that stack too. And I'm never going to see that, and you're never going to see that, but somebody's going to see that, and let's hope they're not dead, right? Okay, we can also save RAM by not using pointers, right? Like if you're arguing with a C guy, right? And like, how else do you interface with C guys? No, I'm sorry. And you're talking about, okay, I have this array, and I want to save some indexes into it. You know, in C++, you'd save pointers or iterators or something that ends up being a pointer. Whereas in C, you could say, well, I know where that thing lives, and I know how big an element of that array is, so I can just save indexes. And if that's like, you know, less than 256 elements in that array, then I only need to save an 8-bit value to index into an array. Quarter the size, right? And, you know, we could encapsulate this so that we are making a space-optimized pointer, which to the user gets turned back into a pointer when used, right? It's, you know, inlining saves RAM. I'm not sure that, you know, that's usually something that gets, that's the typical argument for inlining, right? But it also saves stack space, right? Doing stuff at compile time obviously saves everything, right? So, you know, okay, we got things to do. We know how to do this better, right? So what can we use, right? Okay, where's the books? Where's the code? Where's the libraries? I'm not good at cricket noises. Like, there is a book from Miro Summik about, you know, programming in a state machine framework rather than using multi-threading. And it's a really good book, but his implementations are all macro hacking. And don't macro hack, please, right? Yeah. So let's look at like the way we actually do things now, right? You know, this is step 7 of a Hello World tutorial, right? So what we're doing is we're initializing a UART, right? We want to set it up and talk to it, right? So, and this is supposed to be somewhat hardware agnostic, right? We want to write this code and then be able to swap out the chip. And this is done in like a split backend is how this is called. Basically, you have like a header file and then swap out the CPP files that actually implement these functions, because on another chip, you're going to be doing it a little bit differently, right? It's going to have different register names or whatever. But we're already breaking that here in the first real line of code on line 7, right? Because you know, there might be a power saving mode of the version of the same chip that where I not only turn on clock, I also turn on power, right? So, okay, C trying to be generic, right? So I set up my UART configuration and configured the UART. Simple enough. Problem is, this is all standard, right? These are all defaults. Like, why do I have to know this stuff? Well, we're using a language that doesn't have constructors, right? So having defaults, yeah, it's not trivial. What else am I doing? Okay, I'm setting up 2 GPIO pins that are going to connect to my UART, right? Like internally in the chip, the UART could connect to that pin or that pin or that pin, and that pin could be connected to either the UART or the analog digital converter or whatever. So there's like a switch network where I can set these things up. And to be honest, I have no idea what this does, like physically, right? I would have to look in the data sheet. And data sheet, like, that sounds trivial, right? But the data sheet's the size of the C++ standard. And it's debatable which one's more complex, right? So that's not trivial. And the question is, like, why do we even have to do that? I mean, yeah. But the biggest problem is I just told you guys not to use schedulers. And here in the hello world, there's an implementation of a blocking call to read, right? I'm reading the UART, and I'm just waiting until there's data there, and then I'm going to return with the data. Here we're using this a bit more, right? You know, okay, this is all obviously something that should be on top level and not hidden in a library, but you can kind of see what we're doing here. We're setting up LED pins, right? And here we're setting up the port speed to 50 megahertz. Remember in the last slide we set it to 2 megahertz. What happens to save us is it's a different port. So if you happen to put your LEDs somewhere else, you'd have a subtle bug that, you know, initialization order. But that's not a bug here, right? I actually also wasn't looking for bugs here. I just want to show you how complex it is, right? And then so, you know, this is kind of standard, like, you know, if you coded in the 80s, no. You know, we're reading data from our UART, and we're parsing it to see if it's help or LED or whatever, and then we're reacting to it and sending data back out, right? This is step 16. I skipped a bunch, like how do you make like write and stuff, right? Okay, because, you know, a Hello World tutorial needs 16 steps at least. And step 17 is obviously because 16 didn't work, right? The system needs to know that when I write to the UART, or when I write to printf, that it's actually connected to that UART and not some other UART and not maybe the USB or whatever, right? Morse code on an LED. And it needs to know like where stuff's coming from, and it needs to know how to set up the heap and that kind of stuff, right? And you know, if you look at this, like SBRK, because that's a good name for a function, dynamically increases the heap size. The heap starts right after the end symbol defined by the linker. Okay, that's safe. And extend it on demand until a collision with the stack pointer is detected. Now that sounds safe, right? What if the heap grows first and then the stack grows? We're screwed, right? So yeah, I mean, this is blatantly out in the open, obvious. Somebody's going to die, and it's in a Hello World tutorial, right? Because we haven't come up with better ways of doing this. So I wasn't looking for a bug, but there is a bug. Like I noticed. Read is blocking, write is blocking, right? So what if somebody says, help, help, right? You know, paste that into a terminal. First help goes out, gets parsed. I'm writing you back the all this stuff in a blocking manner. In the same time, the new help is going into the UART's buffer. The UART's buffer is probably only 3 or 4 or 5 characters deep. I'm going to have a buffer overflow, right? And you know, somebody writing help, help is not the actual thing that happens, but you know, somebody's writing some other command, right? I have 3 commands I want done. I just write them out, right? And since I'm blocking, I get problems, right? So what can we do about this? Well, we could implement it in such a way that, you know, inputs come into some kind of priority queue, get stored in RAM in some way that I don't have to give the same buffer for that, but there's not a library for that, so crickets, right? Or I could make 2 threads, one for sending, one for receiving, right? And the receiving one sits around until it's got something to read, and the sending one sends stuff until it gets more commands from the receiving one. So I have, you know, locking between 2 threads in a Hello World example, because, you know, locking between 2 threads, that's like beginner stuff, right? But I still have a potential bug, right? What about starvation, right? What if something else is doing something for long enough that my buffer overflows even though it has its own thread, because the scheduler didn't come around to that thread fast enough, right? It's pretty much impossible to prove. Like, even if I would, you know, forget 40K, even if I had like a whole lot of money, it would be very hard to prove that that will never happen, even though, you know, if you use a processor that just does terminal commands and make it fast enough to run Doom, it's probably not going to happen, but it's not really provable, right? And if it's not really provable, then, okay, somebody's going to die, right? So yeah, the real solution to this is use interrupts, right? Every time I get a character over the UART, I call an interrupt service routine, and it puts it in a bigger buffer. A buffer that's big enough, because that's really easy to determine, right? So, yeah, we need to go at this in a different way, because we can't, I mean, essentially in every other domain we assume endless RAM. And here we can't assume endless RAM. So, I mean, yeah, we notice that we don't have enough RAM very quickly. And yeah, we also filled up the chip. Like, okay, this is debug mode, so this is going down. But you know, the next smaller cousin of the chip, we would have filled up with hello world, right? As in, not just RAM, but also like memory, flash. Now, why is that? Well, we were calling into these other functions to configure things with data, two different compilation units. If you don't turn on link time optimization, that other compilation unit will have to instantiate every possible configuration because it doesn't know what data you sent, even though it was known at compile time. And again, if you turn on link time optimization, you're screwed because nobody understands volatile. So we also have things like sprintf, fprintf, something else, scanf, whatever, like C library stuff that was put in here, and it's the same problem again, right? Remember, scanf, okay, we just want to read 31 characters and stop at white space. That's not hard to do, but they have to instantiate the whole everything because the CLib doesn't know that this is our string, right? Again, C trying to be generic. Efficient language until you actually try to do stuff with it because you don't have the tools to express that in an efficient way, right? So, yeah, I mean, scanf, again, like scanf, that's this, right? You know, in this particular use case, I'm reading till I find white space, right? Or I get to the end of my buffer. And printf is basically just a loop, right? We're not even formatting in our printfs here, right? So we could have done that way more efficiently, but it meant we'd have to implement things by hand, which is usually what ends up happening, right? We don't use libraries because they're not efficient, because we used an efficient language, right? There are other ways to do this. Let's look at the inherent complexity, right? What did we actually specify here? What did we change from defaults, right? Okay, baud rate and which pins we used, right? Baud rate, which pins we used, right? That's the inherent complexity. And if we capture this in this way, okay, underscore baud, that's using the same thing, you know, Hannah uses to do this underscore C, or parsing user-defined literal at compile time, typing coding it, and dropping it into this factory function. I know I don't have time to explain how all that works, right? Especially like what happens in this template monster here that makes me a UART with everything that I knew at compile time hard-coded into it, right? But it is possible. Also, initialization, right? You know, we were turning on port C. Port C is a big port. There's like 32 pins on port C. There's probably 32 other things turning on port C. So the optimizer should be able to get rid of them, right? Well, first of all, no link time optimization. They're all in different translation units. Second of all, they're marked volatile, because otherwise the optimizer could just not write anything to it because it can prove we were never reading from it, right? So volatile is too blunt of a tool. Last year's talk, my quasi library, I alluded at how we could solve this by doing our own optimization, because we understand things better than the compiler in template metaprogramming at compile time, right? So everything goes into this init, and we look, okay, what are you initting? Well, we're going to sort that by address, and everything that's in the same register, we're going to just move it together, and then sorting by address also helps us because we can write to that thing, and then we can write with offset to the next thing, because loading a unique 32-bit address, if you have a 16-bit instruction set, takes a couple of instructions. But if I can just store with offset, then that's way more efficient, right? So I know more about my program than the compiler does, and I can write my own code generator and optimizer that runs at compile time within the type system. Okay, using run to completion, right? Sikasomic's book's about this thick, but this is essentially the implementation of a good part of that book, right? I have an event queue in which I drop all my events that my system has, right? I specify another thing that in my UART, right? Last time I just specified to here. Here I say, okay, when you get a byte in your interrupt service routine, do this. Post this event to the event queue. Now, this is all just a type that results from this, right? I'm not actually passing back data. It's the same strategy used in a lot of Boost HANA. All this is just type information being passed back to the template monster that lives in here, and he's going to build me a UART object that does that. That's why I had to say auto, because that's going to be a really ugly type, right? I can also specify out pin, initialize everything. It's going to be all smushed together and optimized. And then this parsing of like help and whatever, what's the inherent complexity of that, right? We shouldn't have been doing like scanf, printf. We should have been doing something more like boost parameters. I don't know who's used boost parameters, but essentially you say, okay, these are my command line arguments, and these are the arguments that they take. Yeah?
It says 0.9 for both.
0 to, yeah, I was getting to that. That is the piece of domain-specific knowledge that we need here, because our code generator is not perfect. It's actually port A pin 9. I could do 0xA9 and parse it, but a literal can't start with a letter, and ports are a letter, right? And so, yeah, it's 0.9. It's actually being parsed into a port and a pin. This is all going into type information and eventually turning into calls to registers with, taking into account which chip we're on, right? Because it's going to be different for different chips. But anyway, this should essentially be a factory for a boost parameter-like thing. This hasn't been written yet, but I know that it is possible, right? And if you think about it, it doesn't actually even have to store the buffer, right? Remember, we had a buffer for our input, and then we were matching against it. It could be implemented as a state machine and not need a buffer, right? Every character that comes, I switch states. Oh, I could be in that command or that command. Oh, I'm in that command now. I'm sure I'm in that command. I just have to wait till he's done that command. Oh, wait, he said something wrong. Error, right? So I can do that much more RAM efficiently. And here, process Q. Okay, when I have this, then do that, right? Lambdas are sexy. This doesn't quite work that way, right? This would be cool if this worked that way. The problem here is, this syntax is sexy because we have ranges, right? If I were just trying to do this with iterators, then this would be much worse, right? So each of these objects, my command parser and my UART are convertible to a range, and so I can just say, take the stuff from that, put that in that, right? And this is the big potential I see for ranges in embedded bare metal systems glue code, right? You can make your glue code look good, and you have to glue a lot of different stuff together, right? This doesn't quite work as expected because remember the UART's buffer was only a couple of characters deep. We're going to overflow it here because we're sending, we're writing a bunch of stuff to it all at the same time. But that's the beauty of ranges v3. An output range can fail, right? Using iterators, standard copy from begin and output iterator. Output iterator has to be big enough, and since we have endless memory, we can make it big enough, right? But what if we don't have endless memory? We have to make it so it can fail at some point, right? So this copy returns a pair of the rest of the input range that didn't get into the output range and the output range. Well, we can ignore the output range part of that, but the input range, we need to create a range with this and then store that back into it, right? So write as much as you can, and then set a timer, come back, write as much as you can again, right? We'd have to create another event, another timer object, and so on and so forth, but it is doable. Wouldn't fit on the slide anymore, but it is doable, right? But if, 300 pages of a book fits on a slide, you're raising the level at which you can express yourself. So how does this work, right? Well, hardware already has a buffer that I'm writing into, and it also already has a flag that I can't write anything more into that buffer, right? It's a single pass range, obviously, because once I've written something that FIFO, it's gone, right? But if you notice, okay, get reads, done, well, do I have anything more? Yes, no, right? Next, well, yeah, single pass range, what does that even mean, right? I don't have any state. With iterators, I need state. I need to at least say which iterator is which, right? Are you begin? Are you end? Here, I can do a whole range that's just meta information. Like, okay, if you want that, go look in the hardware there. If you want that, go look in the hardware there. This is, Quasir syntax for reading things. That was last year's talk. So C++, modern C++ is great for microcontrollers, right? Not really. I mean, this is a lot of code, and it's ugly, and that's probably good that it's ugly because it's also bad. Very domain-specific problem. I have a big packet that I want to send over the CAN bus. CAN bus packets are only 8 bytes, or 0 to 8 bytes, right? So if I want to glue a bunch of them together into one big packet, I'm going to need some kind of, sequencing, whatever. So the way most protocols work, the first byte is some magic number saying I'm not the last, or I'm part of a multi-byte, packet transfer, and the other one's like some counter that counts around in a circle, right? So that's what this counter is doing. It's counting up, and once it gets to F, then it goes back to 0, and we're putting B because B is like I'm a part of a multi-packet transfer, right? So I'm taking, my input data and turning it into a lot of CAN packets. And, the way you do that, okay, I have a deck of vectors, right? Problem is, how big is a CAN packet? Well, 0 to 8 bytes. How big is a vector? As in total RAM cost, right? 3 pointers on the stack, right? And then heap part with bookkeeping, with heap fragmentation penalty. I probably, quadrupled the amount of RAM that I need, right? Okay, we were bashing C guys earlier, but we got to do our homework too, right? The other thing is, if I'm copying from like this input buffer into a lot of packets, and then those packets into CAN hardware so that it gets sent, I'm copying one time too many, right? I should be formatting each packet and copying it directly into hardware. CAN FIFO is 2 or 3 packets deep, right? I can't put the whole packet in there all at once. So not only is obviously the counter an endless range, right? Starts at B0, counts all the way up to BF, and then back to B0, around in circles forever. And I have ranges, so I can express this as an endless range. Way more efficient than I could with iterators, right? But also, I have the potential of being lazy, right? I mean, other stuff in here would also get easier. I'm copying 5 in here, and then here I want to copy up to 7, or if I'm at the end of the packet, right? And yeah, with ranges, I could just say copy till you're full, and your capacity is 8 bytes. And then either the output's full or the input's empty, right? Here, there's actually a bug. What if my packet's smaller than 5? Okay, I already copied too many. I should have been doing a min here as well, but that wouldn't fit on the slide, right? So if we think about, I have a copy, and I'm just going to pipe onto that CAN packet formatter, right? That's sexy enough that that doesn't even actually have to live here, right? It could live outside. I could just have send one packet, and then somebody could, in a lazy way, just keep writing to that, right? Because I have another problem here. If I wanted to be lazy, I'd have to make in live longer than this function, right? I mean, if I wanted to return from this function, then later parse the next packet, send it out, right? I don't know how big T is, so I'd have to type erase it if I wanted to save it here in any way. But whoever called me, he knows how big T is. So if I can take the complexity from inside, put it in a range adapter, right? Then it could be used outside without polluting the caller's code, right? So I have the potential of being lazy in many ways that I wasn't previously able to be lazy. So, in conclusion to that, like there's a lot of inefficiency myths in the microcontroller community, right? People that use C and say, yeah, I tried C++ and it filled up all my RAM and it did. And the thing is, like, if you turn on exceptions, you're probably already out of RAM, right? Because the emergency buffer is bigger than your RAM, right? The emergency buffer is the thing where the exception goes when you throw out of memory, because it can't go on the heap because that's out of memory, right? So it saves an extra buffer, right? And there's a lot of things that you can do terribly inefficiently in C++. That's not the way to look at it, though. We have to look at it we have a tool set which allows us to express ourselves in a much better way. And if we can express ourselves in a much better way, we can build domain-specific idioms, domain-specific algorithms and patterns. And the thing that's kind of revolutionary in my mind about ranges is we can just use that, right? Like, it's one of the only things we can actually use. I mean, if you throw out exception, if you throw out the heap, if you throw out all that stuff, there's not much left from the standard library you can use, right? Can't have virtuals, can't use the heap. Well, you could use allocators because that's fun, right? So, yeah, finally we have something that's just based on a concept. And, hats off to Eric Niebler and Sean Parent for making this like a concept that happens to have an implementation rather than we implemented it and then specified that, right? I mean, that's one of the reasons why ranges are so pure. And that's one of the reasons why we can use them, because their intellectual purity is very high. And that allows us to program in a way where we don't have to spend years onboarding. Like, if you come from C++ background into embedded, they're going to have to teach you a lot of stuff before you don't break things, right? There's a lot of indigenous knowledge, domain-specific knowledge, and we can encapsulate that, and even how those encapsulated things talk to each other can be relatively normal. Okay, what can we do about it, right? Like, what can we do about this problem? Rather than a vector, we can use a static vector, which is in SG14. It's basically a vector that can only grow to a certain size. And after that, the world ends, right? Just have to make sure and not grow further than that. So it's essentially a standard array, but it also has a size, right? Because like a standard array, it's just that many bytes, and you have to use exactly that many bytes, right? You can't say I have a standard array with a capacity of 4, but I'm only using 1, right? You couldn't really interface with that kind of container in the past because an output iterator can't fail, right? If you're copying into something that's not endless, then it can never be full. Whereas with ranges, it can be full. The result of I copied something into something and my thing that I'm copying in there is bigger than it can hold is I get the rest back as the pair that's returned from that algorithm, right? I can also do memory pools. Like, I mean, this is another example of innovation valley of death. Like, the buddy algorithm is like as old as my dad, right? But it actually works very well in microcontrollers, right? And okay, maybe you want to do like a load balanced buddy algorithm where you say, okay, I don't just divide by 2 every time I need a smaller thing. I look at all the types that I'm going to be putting in there and make like a balanced algorithm where if I have like one big one and then the smaller ones are like a 1/12 of that, then I divide by 12, right? And I can do this at compile time. If you give me all your types, I can make the best load balanced pool. I can also make flat out, you tell me how big and how many elements fit in it. That's obviously also possible, right? We can use state machines, put storage in states rather than on the heap. More deterministic, usually maps to what we're doing better than just putting it in a bag and saying, at some point I'm going to tell you, here it is again, right? We can be lazy, right? With the CAN example, we can save a lot of RAM. We can save a lot of different packet sizes if we say, okay, a CAN packet only ever exists as an input to a state machine or an output to hardware that was lazy generated on the fly. Then I don't need a pool in that size category, right? Oops, not working anymore. So how do ranges help us with that, right? Well, it's mostly about glue code, right? If I'm taking something from here and putting something in there, the most intellectually pure way of expressing that is with a range. Iterators don't really cut it. We also need a certain amount of type erasure, right? Like everything I've shown you so far was heavily templated, and that doesn't work very well across compilation unit boundaries. I can't say like extern in this template thing. I can't forward declare templates in a header of another translation unit, right? So if I have some contiguous container and you can read from a contiguous container, I can make a view 2 pointers, right? Very generic. I have, data-based type erasure rather than virtual functions or something. I can say, okay, begin is there, end is there, here you go. You don't have to know that that was like a node and a linked list, that it comes from a pool and blah, 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 all the stuff that's known in that translation unit. That other translation, you should just say, okay, I increment that one until it's there, right? So because we can use cheap type erasure, I mean comparatively super cheap type erasure, we can talk to other translation units better. I already touched on eliminating buffers, but there's also a category of buffers, right? There's buffers where I don't know how big it's going to be, right? sprintf, how big is that result going to be? Well, if you got 5 doubles in there, it could be very small or very long, right? And that's the one thing that we don't have a solution for if we take away the heap, right? I mean, we can use pools more deterministically, we can use state local storage, we can move things to globals. That's something that's really hard, right? Because the buffer has to be big enough. Well, how big is big enough? Well, endless, right? But we can do that lazy, right? Because those things used to be doubles, right? I mean, our microcontroller, probably not doubles, probably ints, but same problem, just not as long. But they used to be ints. And I can again generate a state machine that holds like a tuple of whatever my inputs were and goes through my format string thing by thing. Whenever it finds like a placeholder, says, okay, I'm at tuple element number 1. How do I parse that into some small local that just has to be as big as an int can be in a string and not the whole string? Go through that till I get to the end, go back into the parsing string. So I can have a lazy format or lazy can packet generator or lazy other things, right? And this is quite complex stuff. I mean, I think Eric Niebuhr several years ago said someone should build this. And if you are building it, please, please, please contact me. I don't want to do this, right? But, oh, my thing doesn't work anymore. Embedded system, no. Here's how I do it if I end up having to do it, right? Format string, obviously const expr, right? I mean, we can debate how we define like a placeholder, but this is like Python, right? And everybody loves Python. Actually, that was not sarcastic. First time today. We have, our formatting, how to format it, shouldn't go in the string. It should go onto the parameter, because we can add, meta information to data quite easily. Save all those in a tuple, make it into a range, right? Lazy formatting, well, we'd have to generate like a state machine, right? I go through these things, tell them either at the end or I find like an open curly, right? The point where I find an open curly, we'll have to defer to my second state machine, which is stepping through the tuple, right? I know what position in the tuple I am, because at compile time I can go through that string and find out where all the delimiters are and store that in a compile time readable manner. So I know which tuple index corresponds to my index in the const expr string, right? And then all I have to do is generate a switch where I put all those things in the case, right? It'd probably have to be if else. I don't know, might be able to do it in a switch. Anyway, it doesn't really matter. I switch into which position I'm at, take that, format it into the buffer. I can even make the buffer smaller than that and format it several times, shifting it back and forth to match the buffer, right? Go through my buffer format at the end. Well, I will need another index, but that could be an 8-bit value. when I'm at the end, do the next thing. When I'm at the end, do the next thing. And yeah, essentially, if you got really creative, you could put like buffer, then tuple, and as you eat values out of the tuple, if it was a single pass range, you could corrupt it by making your buffer bigger successively, right? You could also like reorder the input arguments into like, when I format this, this will be the smallest, so that you grow your buffer sooner. Like, as soon as we have a good public interface, as in the user expressed their intent, and it's all in a way that we can read it at compile time and work on it at compile time. I mean, this is like, you know, people talk a lot about from C to C++ as, oh, that's a revolution, whatever. I think from C++ to C++ 11 and the, you know, metaprogramming development that's been going on since then, I mean, people don't really understand. Like, back in the day, you used your compiler using Boost MPL or Fusion or Spirit or whatever, and you hit compile and went and got coffee, even though this was just like 2 pages of code, right? I mean, this has gotten 2 orders of magnitude faster. And I think we can do a third, right? There's some proof of concept stuff that could make this even faster. So it's 1,000 times faster than that old thing. Plus, way more expressive, so you probably could find algorithm complexity improvements in your user code because it's not just a huge hack, right? So we can actually do these things now, and we can improve on them iteratively later. We just have to make the public interface all be compile time readable. So how far are we in this, right? Well, we have the hardware layer pretty well buttoned down, as in works, and there's a code generator for every chip, but shit in, shit out. A lot of the chip manufacturers don't specify their chips correctly because we're the only ones using it, right? Well, the debugger is as well, but you know, those bugger forks usually don't get filed if some obscure thing that you never read is formatted the wrong way, right? If it has twice as many bits, well, okay, right? But if we have twice as many bits, we write twice as many bits, which, you know, could corrupt something or whatever. So there are quality issues still. But as far as, you know, taking the user input of, you know, read, write, initialize, whatever, that already works, right? It's actually quite simple. It's just sort at compile time, and then you run a fold, taking all the things that are next to each other, look if you can merge them, and the checking if it's actually legal to do this, like am I writing to a reserved bit, or am I reading from a write-only value or something, you can do that in the factory functions quite easily, right? We actually want to do a whole lot more optimization stuff. So this is a correction on my talk from last year. You can do that, but not on every chip, because it seems like with, you know, as we find optimization potential that you couldn't previously express because it would be totally ugly code, well, most of the time nobody ever did that, right? And so there are bugs in the hardware. Like, you should theoretically be able to read 8 bits out of a 32-bit register, right? You know, byte addressing is theoretically possible on, but if you do that, maybe you'll get a different value, or maybe you'll get all zeros, or, you know, there are some weird bugs. So we took away all the aggressive optimization stuff because we ended up not needing it. Just sorting by address and merging things together and doing init all in one place. Like, we've been porting stuff from embed and it shrunk like 5x, right? We don't need all the, you know, it's more efficient than C because they're trying to be generic in C, and that's not what C was built for. And so they've snuck in enough inefficiencies that way that, okay, right? So, questions?
Just a second.
Yeah.
I have a question regarding your first example.
Mm-hmm.
DST processor setting the UART, etc. Suppose I was
This one?
suppose I was to use your well, even
Here.
yeah.
Yeah.
Suppose I was to use your library,
Yeah.
which set everything. I would have it's a practical question. I would have lost all the underlying libraries that are available to me, for example, from STM, the STM Cube, or all the things that enable me today to move from one processor to another in a wide range of processors. I would use in the same question regarding the CAN example. I don't want to write CAN packeting and CAN open the layer, data link layer by myself.
Well, if somebody else wrote it, then yeah, it's good to use the thing that somebody else wrote.
Yeah.
But essentially, if you're using the CubeMX, that's a code generator too. It's just an external one. It's not in C++, right? And you can still use it in hybrid, right? You have to turn on C++ 11, which, to be honest, I don't know if that still works with the QMX stuff that they generate. If it doesn't, well, that's already an argument against that, right? But you could say, okay, I'm going to generate some of my peripherals, and I'm going to use this to do other peripherals. But there's not a whole lot of lock-in here, right? Like, if that's what you want, you just swap out the include file that defines the UART, and in a perfect world, somebody's also implemented that too. This is not a perfect world, and we're a tiny, tiny company, right? But you know, on a theoretical level, CubeMX versus this, I can swap out the chips and get another implementation that builds me a UART out of that same information, right? Because I'd reduced it to all the relevant information for this use case, and then I just switch out the code generator, just like you're doing QNX. I mean, like I said in the beginning, we're in the middle of the innovation valley of death, right? So if you have to ship a product 6 months, then use CubeMX, right? Because people put, I don't know, 100,000 man years in it, probably not. Maybe, definitely many man years into it, right? I mean, this stuff is essentially 2.5 man years, right? Cumulative, right? We're at the beginning here, but what if you want to switch to a chip that is not part of QMX, right? This would still work as an open source rather than, I mean, QMX is basically all about vendor lock-in, right? As soon as you start, you can't switch to another. Or what if you, like in CubeMX, what if you want to deep sleep, right? What if you want to power your processor down so far that only part of the RAM is persistent and all the other stuff will be corrupted, right? I mean, that would have worked really wonders here, right? Battery died. That wasn't actually even on purpose. So if you want to deep sleep, then how do you organize your memory so that all the stuff that you need after the deep sleep is in that area? Well, you could do that by hand. And then how do you tell if you're in some state where you could deep sleep, where the rest is irrelevant? Well, if you think about a state machine, that maps very well, right? You have some base state, and if you're in that base state, well, then you can sleep, right? And you just have to make sure that all the state local storage in that base state goes into that part of memory, right? So, I mean, I think these same kind of tools could be used to improve the whole way we write programs in a way that we're more, because essentially CubeMX, they have a limited amount of customization points. I mean, they don't want to put a bunch of ugly code into your repository, right? You're using CubeMX, you still want to say, oh, that guy committed this, I understand that. And that's the problem with external code generators, right? So either you say, okay, I'm going to put all sorts, I'm going to have like 2 systems essentially where I have to look at commit stuff here and in that other file, or I use very non-intrusive customization points, at which point I'm giving up a lot of flexibility, a lot of optimization potential, and so on and so forth. So I think C++ internal code generator trumps C++ external code generator. It's just harder to write the C++ internal generator, but it's getting easier.
So it's a practical question. Suppose today we are doing, we are upgrading a version of the CubeMX we are using.
Yeah.
Instead of that, would it be feasible to try this type, your implementation? Is it
not today?
Great?
No, not today. And how long it's not possible depends on how we end up funding this, right? Like we're 6 nerds in our company, and this is what we do in our free time and a little bit of our work time because we want it to like work, right? And that's why it's only 2.5 man years, right? If we had like a sugar daddy company, like, I mean, think about how much money went into making it easy to write apps for cell phones, right? I mean, that was many, many nerd years, right? And, you know, if somebody drops money on it, we could scale up quickly, and, you know, it would be still a year or two before you'd have pretty comprehensive coverage, because we'd have to write a lot of, you know, it would be a similar amount of man hours that went into CubeMX, but it would be a better system. So release early and often, I warned you at the beginning.
Another question.
Yeah.
Wondering if you have tried to use, for example, Bruce Spirit to decode this lazy range and encode the lazy range.
Use what?
Spirit, Bruce Spirit.
Bruce Spirit.
Yeah.
You could do it. Well, you wouldn't. The problem is that you know, Bruce Spirit is good for like parsing input and formatting output, but not without like knowing what it's going to format in a more. Actually, no, you probably could do it, but I mean, just that trivial example would probably take like a whole coffee break to compile. But it is in theory pretty much the same thing, which is another reason why it. I mean, I kind of do know why. Like, I don't know the exact status of like the Boost Spirit library. Many of the Boost libraries in general, I mean, now that David's gone, like a lot of them are like Boost MSM. Okay, Chris Uziak, wherever he is, was grand enough to actually replace that with something maintainable. But most of the Boost libraries, there's not a lot of code ownership there, right? And yeah, so you could do it with Boost Spirit. And that should be just like, okay, drop in, take that, put it in like modern C++ and whatever, but yeah.
It is not only Bruce Spirit. What I mean is the algorithm we are using, recursive descendant parser.
Yeah. Yes, I mean, your point is correct that the algorithms are already there. I mean, I've looked into Boost MSM relatively, you know, deeply, and I've looked into some other Boost libraries relatively deeply. I haven't looked very deeply into Spirit. I've looked into MPL very deeply. I think understanding how Spirit does it would be more work for me than just writing it, right?
Any more questions?
Because we metaprogrammed in a very different way in that era, right?
Okay. The last one.
So I see just one big problem with using all this.
Yeah.
And that is for microcontrollers, especially in the commercial field, you have about one compiler that actually supports C++ 11 and up, and that is GCC, and you won't get many of the bigger companies really excited about using an open source compiler.
Yes. You know, Clang is getting there, but I mean, the reason they have compiler lock-in is because their compilers are terrible, right? I mean, okay, being on a theoretical, you know, intellectual level right has no influence, obviously, right? What will have influence is if, you know, people entering the field, startups or, you know, innovative companies, not some of the typical European companies. I don't see them innovating in this field very much. I could be wrong. I could just be blind. But if new companies come in and have success with it, then it will change very quickly, right? I mean, I think, you know, there were some technologies on the iPhone, for example, that BlackBerry found like, oh, you're never going to be able to build phones. You're never going to be able to, and then they just did it better, and now look at BlackBerry, right? I think, you know, there can be pressure if people are having success with it. But yeah, that's, I mean, we're kind of concentrating on building it first. But yeah.
In Express Project have a new version now, which supports
Wow, is it based on Clang or is it?
I don't know. I am waiting for a license for it. I'm a part of I'm a part of the combination, so I know it's there, it exists.
Yeah. I mean, I'd be very surprised if another compiler came in and actually implemented the template metaprogramming stuff, because I think the complexity of that is like an order of magnitude larger than the normal traditional part of the language. I mean, I'm not a compiler guy, but as far as I understand it, like if you look at how long it took to put new stuff in, a library feature here and there or whatever, but if you want to fundamentally add, add handlers for corner cases and metaprogramming, that tends to take a while. We're done? Okay.
Thanks for the brilliant conversation.